What are you having trouble with? Anything? Everything's going okay in terms of the stuff? Yeah.
We did like Avogadro law, and then there's oxygen gas and the ozone gas. So this one, it was about Avogadro, right?
About what?
Avogadro law.
Yeah.
So it says increasing laws. So we're just looking like here, 3 and 2 says decreasing. We're
Right.
looking in here.
That's right. Because it's not about the number. So the question is about, going back to gases, talking about Avogadro's law, that the volume is dependent on the number of moles. So that's number of moles of gas molecules or gas atoms, not atoms within a molecule. So we had that example here. There. Avogadro's law, where we have 3 moles of oxygen going to 2 moles of oxygen. That being a change in volume, even though the mass actually stays the same and the number of oxygen atoms stay the same. But because once a bunch of atoms form a molecule, even a pretty large molecule, if it's a gas, the size of that molecule no longer matters because the sizes between molecules, the spaces between molecules are so great. So we can kind of ignore that and say that 3 gas molecules have turned into 2 gas molecules. And so that's the decrease in volume. That's where it comes from. It doesn't matter how big the molecules are. That's what the kinetic molecular theory tells us.
Can you explain once again Boyle's law?
While we're in here, Boyle's law tells us that there's an inverse relationship between pressure and volume. So one goes up, the other goes down. That's all. I mean, that's really all there is to it. We can explain why Boyle's law happens looking at the kinetic molecular theory by saying that if volume increases, then, and the particles are still moving the same speed, the same temperature, then there's more space in the room and the particles are less likely to hit the wall or are going to hit the wall less often. All right, what else? As you know, we have an exam on Tuesday, so that'll be during the lab time. The class time we'll still have before that here. We're not going to go into any new stuff. We'll just use that time like we did last time for last minute questions or studying or whatever. If you need some help from me, I'll be in my office tomorrow, normal office hours. I should be there all morning. So you're welcome to drop by if you have questions. Hopefully the studying's going okay. Hopefully. A couple people have asked kind of what to study, what's the key stuff. The key stuff is really the problems in the book. If you can do the homework in every chapter as it's suggested on Blackboard, you should be good because the exam's going to look pretty much like that. The only exception to that would be this gas stuff where you just kind of have to keep these laws straight, as we've talked about, because there aren't really good problems for that in the book. The book focuses more on the math.
Laws by name, or is it okay if we know the concept of them?
Yeah, it's according to the objectives specifically, you should know them by name. I don't care about that, so I tend not to ask those sorts of questions. I think if you understand the relationship between pressure and volume, who cares if you know that it's called Boyle's law or not? Like, no offense to Boyle, but we care more about what the molecules are doing than who figured it out. So I would say don't worry about the names. I'm not going to ask about that. All right, so let's talk about the last bit of this chapter that will be on the exam. And there's really just a couple things we haven't talked about. One is the final measure of concentration, which you actually did on Tuesday in lab anyway, which is molarity. And then we'll talk about osmotic pressure and how solutions behave in biological environments, like in the bloodstream and that kind of thing. All right. So first, let's talk about molarity. I know this was in the lab, but it's very important. measure so we can spend some special time with it. Molarity is just another measure of concentration, but rather than being dependent on a mass or a volume, it's dependent on a count of particles. And the way we count particles in chemistry is through the mole. So it's defined as moles of solute divided by liters of solution. So it's moles per volume. That also reminds me, I have your quizzes graded, but I forgot to bring them down. So if you want your quiz before Tuesday, follow me upstairs after class, and I'll get it for you. Another way we can express this is moles divided by liters. So you take the moles of solute, you divide by the total liters of solution. And the way that's usually reported as a unit is a big M for molarity, just a capital M. All right, so let's practice calculating a solution's molarity. Let's say we have, I used these numbers before, 4.78 grams of sodium chloride. This is kind of like the lab that we did on Tuesday where you boiled off the water in 25.00 milliliters of solution. So if you have a mass, you have a volume, we can always do those conversions the way that we've always done them before. So the equation for molarity tells us that it has to be moles divided by liters. We have grams and milliliters, so we'll have to convert each of those. Milliliters is simple enough. How many liters is 25 milliliters? Yeah, we just move that decimal place over 3 spots, or divide by 1,000. That's going to be 0.02500 liters. But then to convert the grams to moles is a little more complicated. We need to use the molar mass. So we need to take that 4.78 grams of sodium chloride and get a conversion factor that tells us that relates grams of sodium chloride to moles of sodium chloride. To do that, we look to the periodic table. We add up those masses. So sodium is 23 and chloride is 35.5. That's 58.5 together. Grams cancel and we're left with moles. I did that calculation and I got 0.0817 moles of NaCl. All right, so now we've got moles and we've got liters, so we can get molarity. So the molarity is the moles, 0.0817 moles of solute, NaCl, divided by the liters of solution, which is 0.02500 liters. And we get 3.27 M, which we call molar. So we would say this solution is 3.27 molar sodium chloride solution in water. And other ways that we can write that using those units is understanding that molar is moles per liter. So we could say 3.27 moles per liter, same thing, or 3.27 moles per 1 liter. Those are all ways of saying the same thing. Molarity is important for us for a couple reasons. One, in chemistry, when we're talking about things like calculating how much of something we need for a chemical reaction, we usually do that in moles because that relates to the chemical equation. The chemical equation tells us a ratio of counting things, and so we need moles to do that. So if we have a solution that's in like percent mass by volume, we'd have to do some math to figure out how many moles that is for how much solution we would need for a particular reaction. If it's in molarity, it's pretty simple. We just multiply it by the volume and we've got moles. So that's helpful in that way. Another reason this is helpful is it allows us to count the number of particles in solution. And the number of particles in solution is really important for things like electrolyte balance, which we'll talk about in a minute, and osmotic pressure. So let's try one more practice problem going the other way. And let's look at how we can convert between different units. I think this is a problem that's in the lab also. Let's say we have a 0.9% sodium chloride solution. And sorry, that's 0.9% mass by volume, M over V. Does anybody know what's special about that number? Why did I pick that? Why? What's 0.9% NaCl?
Human.
What? Because it was in the lab? Yeah, well, it was in the lab for a reason too. This is what we call normal saline. So if you have a, what? Yeah, like would go in your blood. If you get one of those bags, like an IV bag that says saline solution, that's what this is. Or eye drops that are saline solution, that's what this is. So this is what we call normal saline. It has a special biological significance that we'll get into in a little bit. But I want to know, if we have that, what is the molarity? So what is the concentration in molarity? How would we do that? How would we take a 0.9% and get that into molarity? Any ideas? We kind of have to go back and talk about what that means. So when we say 0.9% mass by volume, what units are we actually talking about? And if you don't remember, it's what? Yeah, it's grams per 100 milliliters is another way of thinking about that, or grams divided by milliliters times 100, however you want to think about that. So 0.9% NaCl, mass by volume NaCl, is really saying 0.9 grams per 100 milliliters. That's why it's a percent mass by volume. Percent, that word percent, means in each 100 of something, so per 100 of something. So if it's 0.9% mass by volume, that's 0.9 grams per 100 milliliters. When it's written this way, it should be a little clearer how we have a similar situation to what we just did. We have a mass, we have a volume. We can convert the mass to moles, we can convert the volume to liters, divide those two, and we've got the molarity. So let's do that. So remembering that our molarity is moles per liter. That means we've got to go grams to moles and milliliters to liters and then divide those two. So 0.9 grams of NaCl we can convert to moles in the same way. Please make sure to review these mole conversions and calculations for the exam. This will definitely be on there. So that's the same number, which was 58.5 per 1 mole. And that comes out to 0.0153 moles of NaCl. 100 milliliters is how many liters?
.1.
0.1, yeah. You divide 100 by 1,000, you got 0.1. So now we've got moles and we've got liters, so we can get molarity. We're dividing by 0.1, we just move the decimal over 1, and that's 0.153 molar NaCl. That's another way of expressing the concentration. All right, so now before we talk about the osmotic pressure, we have to just have a couple more definitions of things that are related to solutions, but not quite the same thing. And that is suspensions and colloids. Have you heard of those before? Maybe, maybe not. They're a little different from solutions in that they're generally cloudy. So solutions you can see all the way through usually. They're clear. They might be colored, but they're clear. Suspensions and colloids are usually cloudy. You can tell there's something kind of floating around. Sometimes you can't tell there's something floating around, but they're still kind of cloudy. And this is all a function of particle size. So in a solution, which is what we've been talking about so far, the particles are super tiny, like to the individual atom or molecule sometimes. In a colloid, those particles are a little bit bigger. And then a suspension, they're bigger still. The way we tell these two things apart, the way that they're different, is that suspensions will usually settle. Meaning that the particles are so big that if you just let it sit for a while, all the particles will settle to the bottom of the container. And that's usually marking a suspension. So anything that you have, food type stuff that says shake well before serving, that's a suspension, because when it's sitting there, all of the particles have come to the ground or have gotten to the bottom of the container, and so you need to shake them back up to disperse the particles.
Is there any other way to tell, because it could be an over-exaggerated solution because of its sound?
Yeah, good point. So you could actually you could take a saturated solution, add more in there, and make a suspension that had more of it there. The solution part itself would still be the solution part, but the fact that there's more junk in there could make it a suspension also. A lot of medications are compounded as suspensions, especially for kids, because they can't swallow a pill, so you disperse it in a liquid that tastes sweet but gross, and then they'll sometimes eat it or just spit it in your face, which also happens a lot. And then the other thing with suspensions is they can usually be filtered. The particles are big enough that if you pass a suspension through filter paper, like a coffee filter or that kind of thing, or the papers we've used in lab, the particles will stay on top of the paper and the liquid will pass through. So that's usually markers of a suspension. A colloid has even smaller particles. And the way that we can deal with those particles of that size, these usually can only be separated by what we call a semi-permeable membrane. A semi-permeable membrane is a material that has very, very, very small holes or paths through it, so that only very small molecules like those in solution can get through. And we're going to do this in lab in 2 weeks after the exam, but we will be able to separate large molecules like starches and proteins, that kind of thing, using a semi-permeable membrane, and only the really small molecules can get through that membrane, and the bigger colloidal particles like starch and proteins and those sorts of things cannot. So they're left behind. There's a picture of this in the book. I'm not going to pull it in. It's not a wonderful picture, but we'll just look at it briefly. If I can find it. So this is kind of what we're going to be doing next in 2 weeks. We'll pour the solution through the filter, and you'll see that the larger, these red squares, these larger suspension particles are left behind. The solutions and the colloidal particles get through the filter. If we let it settle, the suspension particles settle to the bottom where everything else stays in the liquid. And then if you use this special semi-permeable membrane, which is what we will do, you'll see that the colloidal particles stay inside the bag, inside that membrane, and only the solution particles pass through. Oops. Okay. So let's look at the last idea here, which is osmotic pressure. Has anybody ever heard of osmotic pressure? Do you know what osmosis is? Have you heard that? Yeah, osmosis has to do with the passage of water through a semi-permeable membrane. The reason that semi-permeable membranes are important is that that's what cell walls are, and I'm sorry, cell membranes are. So when we model things passing through a semi-permeable membrane, we often care about that because of the relationship to cells and cell membranes. So let's look at a picture of how osmotic pressure manifests itself through a semi-permeable membrane. This picture in the book here. All right. So imagine you could take a container like a beaker or a jar or something, and you could like separate it through and seal it on the edges. Then you put water on one side, like pure deionized water. On the other side, you put a sucrose solution. Over time, both things can actually pass through the membrane, but let's say in this case, only the water passes through. Over time, the water will try to equal out the concentration. So right now you have, let's say, a low concentration, really zero concentration on the left, and a high concentration on the right of the membrane. So over time, the water tries to equalize those concentrations. In order to make this a lower concentration, more water has to pass through here, because then you got more solvent. So over time, you'll see this side get depleted as more water passes through into this side. And that's what's known as, that's through osmosis. But because you're actually pushing the water level up against the atmospheric pressure, that's really a pressure. It's pushing on that membrane and pushing that water level up against the atmospheric pressure. So that's what we call osmotic pressure. It's kind of like the individual pressure exerted on the membrane by the water molecules pushing through. So we call that osmotic pressure. And we mostly care about this because of what happens in our bloodstream, because of the semi-permeable membranes that surround all of our cells. Because what happens is that if your intercellular environment, your bloodstream, is not balanced correctly with respect to the osmotic pressure, water will either be forced into your cells, which is not great, or water will come out of the cells, also not great. So we want an environment, when we start messing with putting stuff in our bloodstream, we want an environment, or really anywhere in our body, that balances that. And there's a word for that, and that word is isotonic. An isotonic solution we'll have the same osmotic pressure, which is solute concentration, as the intracellular fluid. That's the fluid inside the cells. So a solution with the same osmotic pressure as the fluid inside the cells will not exert a pressure on the cell, so water won't flow into the cell, and it won't exert a negative pressure either, so water won't flow out of the cell. It'll just be balanced. That 0.9% sodium chloride solution is an example of an isotonic solution, and that's why we use it for things like intravenous fluid delivery. The other two extremes of that are called hypotonic and hypertonic. Now, hypo and hyper are common prefixes. Hypo means less or beneath, and hyper means more or above. But in this case, we have to make sure we're talking about the right thing. Hypotonic doesn't mean lower osmotic pressure. It means lower solute concentration. Tonic comes from ionic, comes from ions. So that's what that refers to. So hypotonic is a lower solute concentration, and it leads to an increased osmotic pressure on the cell membranes. And when we talk about solute concentration, I'll give you some numbers in a minute, we're talking about particles, total particles. So it's not like you can have a 0.9 solution sodium chloride and then just also have a bunch of other stuff in there. The total count of the stuff that's dissolved has to be the same as inside the blood, because the osmotic pressure doesn't care what's dissolved exactly. So then hypertonic is the opposite of that. That's a higher solute concentration. Which is going to force water out of the blood cells and cause them to kind of shrivel up. All right, so there's a neat picture in the book that kind of summarizes all this. Right here. And it also talks about what happens to the blood cells when they're in these environments. So your isotonic solution, everything's fine, water can move back and forth, and there's not an increased pressure in one direction relative to the other. This situation is your hypotonic solution, where water is being forced into the cells, which causes them to burst. And that's, that bursting of the cells is known as hemolysis. And then the opposite, the hypertonic solution, water is forced out of the cells, and that's what we call crenation, the kind of shriveling and dehydrating of blood cells.
Okay, what's going to happen when it's going to be dehydrated? What's the next?
They don't work. I don't know.
Just like slowly? Or?
I believe it kills the cells ultimately. So it kills the blood cells, which is why it's a problem. There are some situations where in like emergency medicine where they might purposefully induce one situation or the other because of the systemic effects. Like if you want suddenly a lot more blood volume, you can induce some crenation and pull some of that water out of the blood cells. If you want to get rid of excess fluid really quickly, you might want hemolysis to, you don't actually want to burst the blood cells, but you might want to have a slightly hypotonic environment so that you can decrease some of the fluid volume of the blood. But generally, you're talking about things that are not good for the cells. All right, so let's talk about these numbers and what makes these solutions. We already talked about how the 0.9% mass by volume NaCl is isotonic. Another common isotonic solution when you want some nutrition in it is a 0.3 molar glucose solution. And it's not exactly, it's like 0.306 or something like that, but close to 0.3 is a molarity is isotonic for any particle. Now, the weird thing about this is we already talked about how, we already went through the calculation how 0.9% NaCl is isotonic. But if we, or how that actually equals what was it, 0.153 molar? So if 0.3 molar glucose is isotonic, that means there's a certain number of glucose particles for the solute particles, and 0.153 molar NaCl is isotonic. How can that be? Mass by volume, we expect different things with different molar masses to have different concentrations. You know, they'd be different in percent mass by volume. But molarity should be molarity because it's a count. It doesn't matter how much stuff weighs. So how could the count for sodium chloride be different than for glucose? Any ideas? Why can those have two different molarities and both be isotonic? It looks like the sodium chloride should be about half the concentration of the glucose. So what's happening there?
Different mass.
Yeah, but the mass doesn't affect the count, the number of particles.
Because we have already nitrate in sodium,
Yeah.
so it's going to be, when we give more, so we will have it like hypertonic. Like we will have more inside in our cells.
Oh, to like compensate for it?
Mm-hmm.
Yeah, that's a possibility, but if you're just talking about the solution, like a pure solution related to the cells, they should be the same. So the reason they're the same is that we're kind of using a shorthand assumption here that we really need to think about. When we say a 0.153 molar NaCl solution, the Na and the Cl are not stuck together, right? That's not one particle. That's actually individual sodium ions surrounded by water and individual chloride ions surrounded by water. So a more true way of expressing this is that really this is 0.153 molar of sodium ions and 0.153 molar chloride ions. When we say 0.153 m NaCl, that's just kind of a shorthand to say that, well, we started with the solid NaCl and we put it in solution. But in solution, that sodium and the chloride really have nothing to do with each other. They're totally separate ions. So we have a certain amount of sodium ions, a certain amount of chloride ions. If we add those together, we have about 0.3 molar in total particles. Remember that the osmotic pressure depends on the particles in solution, the number of particles in solution. And for sodium chloride, that's 2 particles per mole. 1 sodium ion and 1 chloride ion. So if we want to talk about the total number of ions, the total number of particles when we care about osmosis and things, we really need to care about all the ions added up together. All right, so that shows that that is indeed the same, because 0.3, 0.306 is about the same thing. That really is the same concentration when we look at total overall particles. All right, let's practice the calculation the other way, see if you can do it. What is 0.3 molar glucose? And the formula for glucose is C6H12O6 in percent mass by volume. So now we have to go the other way. Think about what those units represent. Go back to the conversion we just did, and you're doing it the opposite way. So as we did before, this is kind of a unit conversion. We start in this case with molarity, which is moles per liter. But then our ultimate answer we want in percent mass by volume, which is grams per milliliter, or grams per 100 milliliters. So to do that, we would take first number and make that moles per liter. So that tells us 3 moles of glucose divided by 1 liter. And we can actually do this all together as a conversion, because you can convert units on top and bottom in the same string of factors. So we can come up with a factor that takes moles of glucose and converts it to grams of glucose. And then we can say that there are well, a couple ways we could do this. We can simply say that there's 1 liter per 1,000 milliliters, and then multiply by 100%. Because that's part of that formula. Or we can remember that percent mass by volume is grams per 100 milliliters. And so we could say 0.1 liter per 100 milliliters. And do it that way. Because we know those two are the same thing. So we need a molar mass for glucose. Anybody calculate that? 180? Sounds right. So when I calculate this, I get 0.3 times 180 divided by 1,000 times 100. Should be about 5.4%.
So it's over 1 liter because molarity is always mole over 1?
That's right. Yeah, mole over 1 liter. So that can be really helpful from a solution prep standpoint, that we know, okay, we want to make an isotonic solution of glucose. So an isotonic solution is 0.3 moles per liter. We calculate this out, and that tells us we need a 5.4% solution. So whatever volume we need, we just multiply that by 5.4%, and we know exactly how much glucose we need to weigh out to put in there. As we said last time, the percent measured solutions are much easier to deal with, like in a preparation setting. You know how much you need to weigh out to do it. But molarity can be more useful from a reaction standpoint, of like how much you need for your reaction, or from when we're talking about things like isotonic versus hypo or hypertonic. So we'll want to be able to do both of those, to deal with both of those. All right. The other part of talking about osmosis, kind of the other side of it, is something called dialysis. Well, here, we'll look at this one first. Dialysis is really what we're going to be doing on next in 2 weeks in lab. We'll take a dialysis membrane, which is the semi-permeable membrane, also known as a dialyzing membrane. And it's the same membrane we talked about in terms of osmosis, but now we're saying, well, instead of worrying about the water, let's talk about how the solution particles can pass through this membrane. So the passing of water molecules is called osmosis. The passing of solution particles is called dialysis. Both of these things are happening in these systems. It's just kind of which one are you going to focus on, which one do you care about? So in this case, you put these particles in a bag. So you've got some sodium chloride or glucose type particles. And then you've got some larger particles like proteins or starches, these large molecules, colloidal molecules. Those can't get through this membrane, but the solution particles can. So they'll come out into the solution. Notice they won't all come out into the solution, because ultimately this is an equalizing process. The motion of the molecules is such to make everything equal. So once you have an equal concentration on the outside and on the inside, then you won't change the concentration anymore. They'll be equaled out. But this is the same thing that happens in humans, in our kidneys, or here in artificial dialysis. So your kidneys do this, as you can see here in this picture. your blood comes through these glomerulus. Is that close enough? I don't know. You guys are in physiology and stuff, right? You know this stuff. And that's where the dialysis happens. So that's where the waste molecules in your blood, predominantly urea, but other stuff too, come out through the dialysis through these membranes and then are excreted through the urine. If your kidneys don't work or you don't have kidneys, then you need to do this outside your body. So the blood is passed through some tubes into a dialysis membrane or a dialysis bag, and that is dialyzed, and the particles are dialyzed out there, and that's how you'd get rid of your urea and your other toxic products in your blood. Then the blood, of course, is pumped back into your body after it's been kind of cleaned up that way, and that's why people whose kidneys aren't working properly have to go and do this, have dialysis. So we'll see that in lab in a couple weeks. All right, so a question about this is actually one of the homework questions. Why can't you drink seawater? If you're really thirsty and you're out stuck on a raft in the middle of the ocean or something, you shouldn't drink the water. You shouldn't drink the ocean water, even though you might be super thirsty. Why should you drink the ocean water?
It makes you more dehydrated.
Yeah, it makes you more dehydrated. Why is that?
The water
It's water.
from the body goes out.
Yeah, so it's exactly this idea that we looked this up. Well, let's look it up. So let's find the concentrations of seawater. It's about 3%. Let's see. I mean, assuming these things are correct, who knows? Some research group will assume that it's right. Okay, so this is telling us that there's a lot of stuff in there, but the major components of seawater, of course, salt, it's about 0.5 molar in chloride and 0.4 molar in sodium. And what is the isotonic molar concentration?
It's 5 times up.
Yeah, the isotonic concentration is 0.3 molar, right? Whether it's glucose, whether it's sodium chloride. So if you add all these things together, you're going to get way more than 0.3, right? You're going to get close to 1 molar, probably. But yeah, it's about 1 molar once you add all this stuff together. So 1 molar is way higher than 0.3 molar, which means that that's going to be what kind of environment? Hypertonic or hypotonic?
Hyper.
Hyper. It's over-concentrated. So that's going to draw water out of your cells and dehydrate you. And so that's why you shouldn't drink the water, the seawater, because you don't want to get that much ionic load into your blood and then start pulling water out of your cells. That's actually true of most drinks too, things like Coke. We could probably calculate this. Let's see. Yeah, let's try it. So a can of Coke is, what do you think is going to be the major solute in Coke? Sugar, probably, right? So we'll start with that one. So sugar, yeah. My Coke can here has 39 grams of sugar, and we'll assume that's sucrose. It's high fructose corn syrup, but that's essentially the same thing. And that's in 355 milliliters. It also has 45 milligrams of sodium. So we could probably assume it has about the same of chloride as well. But let's look at the sugar first, because that's clearly quite a bit more. So sucrose is C12 Page 22011. Let me check that. Yeah, all right. And the molecular weight is about 342. All right, so let's look at that. So we've got 39 grams. (342 grams per mole). (0.114 moles). And it's 355 milliliters, so that's a 0.114 divided by 0.355. That's about 0.32 molar. So that's also over the isotonic concentration, especially then if you factor in some sodium and some other stuff dissolved as well. So don't put Coke directly into your blood. That's probably...
What did you do after you
oh, sorry, let me do that more clearly. So I took the 0.114 moles and divided them by the volume, which is 0.355 liters. And that's the concentration. That's the concentration of just the sugar, assuming it's all sucrose, which it's not, but it's a reasonable assumption for our purposes here. So for sodium, we could do the same thing, 45 milligrams. It's going to be much smaller. But we could say 0.045 grams divided by the molar mass of sodium, 58.5, is a very small number of moles. Is that 7.69 times 10 to the minus 4? Oh, that's not right, because that's not sodium chloride. Anyway, that's a small amount, but it'll contribute a little bit to this concentration. And there's not really much else in here. There's some phosphoric acid, and there's the carbonation. So carbon dioxide would be a solute in here as well.
So it's not that harmful. Not as bad.
Well, harmful is relative. I mean, from an osmosis standpoint, you know, it's not like seawater. It's not like trying to drink seawater, but it's probably still not quenching our thirsts the way that water is because of all the other stuff. Yeah. All right. Other questions you want to talk about? No, everybody's good. Excited for the exam?
Sure.
Should be fun.
Mm-hmm.
It's like our Christmas.
Yes. Yeah. It's very exciting.
I don't know about that.
Somebody's looking at this. All right. Well, let me know if you do have questions. I'll be around. I will hopefully not get terribly ill this weekend like I did last weekend, but and I'll be able to answer some emails. So let me know. And come see me in the morning if you want some help in the morning. I'll be here till about noon.